Thank you very much for the invitation and the opportunity to give this talk. So my talk will be about connections between optimization and sampling. So this is a sort of very subjective review of some of the recent results that explore the connections between optimization and sampling that I personally find interesting. There's no pretense of completeness here because the literature is so massive that obviously I can't cover everything. So the problems I'm looking at is suppose that you have a function f from Rd to R, and the first problem is to find the minimizer x star of f, and the second problem is to sample from a distribution mu with density with respect to the Lebesgue measure that is proportional to exponential minus fx. And I will look at 4 different assumptions. So first assumption A is that f is continuously differentiable and convex. So I will always assume this for every algorithm that I will study here. The second, slightly more restrictive assumption is that f is continuously differentiable, convex, and the gradient of fx is m Lipschitz with respect to the Euclidean distance on Rd. The third assumption is that f is continuously differentiable, convex, and small m strongly convex. So if it's twice differentiable, this means that the Hessian is lower bounded by small m times the identity. But in general, without twice differentiability, this is the definition of m strong convexity. And the third assumption, the fourth assumption, D, is that all of the previous ones hold. So it's a continuously differentiable convex, small m strongly convex, and the gradient of fx is capital M Lipschitz. So this is also said to be M smooth, capital M smooth. So now we are going to consider several optimization methods. So first of them is gradient descent. The second is Nesterov accelerated gradient descent. And the third one is heavy ball method. This is by Poyak. Okay, so what we will do is that we will take the step size 10 to 0, and this leads to a continuous limit. ODE limit. And once we have a continuous ODE limit, then we will see that all of these algorithms become quite simple to analyze in terms of a relatively simple Lyapunov function. And if you add the diffusion term, then you get an SDE that targets mu. So, and then if you discretize this SDE, then you end up with MCMC methods that target mu or an approximation of mu. And there's also another way to obtain Markov chains, Monte Carlo methods that target mu from this ODE. This is by the piecewise deterministic MCMC framework. So you add some jumps to the process according to some Poisson rate, and then these jumps will ensure that you are converging to a distribution instead of converging just to a single point, as in the optimization method. So now, first, I'm going to start with the gradient descent. So, all right, it's not very surprising that the continuous limit of the gradient descent is called the gradient flow. Okay, so you have in discrete time I'm not sure. Can you read this, or should I write bigger? It's okay. So sometimes you can make the step size S vary with k, but I just consider this simplest case when you have a fixed step size, and then you are looking at the continuous limit. So when S tends to 0, you obtain the ODE equals to, okay, let's write it this way. Okay, so now the first thing that you check if you have this ODE is what is the derivative of the function itself. So this is gradient fxt d over dt xt, which is simply minus the square of the gradient in norm fxt. So this is a descent method in the sense that it always decreases the value of f. And now, if you define the Lyapunov function Lt as t times fxt minus fx star, okay, plus 1/2 times xt minus x star square. So you have a term from f and a term from the distance to the minimizer. Then you can show that d over dt Lt, okay, equals to t times f xt minus f x star minus gradient of f xt xt minus x star, okay, and minus t times gradient of f xt square, okay, and now using assumption A, okay, so by assumption A we have a convexity. So by convexity this term is going to be bigger than this term. So by assumption A you have this is less than or equal to minus t times gradient of f xt square, and then less than or equal to 0. So it means that t times, given the form of Lt, this implies that t times fxt minus fx star is less than equal to L0, which is equal to 1/2 times x0 minus x star square. So you have fxt minus fx star less than equal to 1/2t times x0 minus x star square. Okay, so you get order 1/t convergence under only continuous differentiability and convexity assumption. So how about having stronger assumptions? So now let's assume C. So you have a M strong convexity. In this case, okay, under C, okay, what we can do is that first note that fy minus fx minus gradient of fx y minus x is greater than or equal to m times x minus y square over 2. Fx minus fy minus gradient of fy x minus y is greater than or equal to m times x minus y square over 2. So if you sum them up, you will get that gradient of fx minus gradient of fy x minus y, okay, is greater than or equal to m times x minus y square. And therefore, trivially, you have, by the Cauchy-Schwarz inequality, gradient of fx minus gradient of fy norm is greater than or equal to m times x minus y norm. And in particular, you know that in the minimum, the gradient is 0. So this implies that if you choose y to be x star, then you get that gradient of fx norm is greater than or equal to m times x minus x star. Okay? So now we also have yes? A here? Yes. So this means that LT is less than or equal to L0. So that is positive. So here in L0 there's no such term because but that is an additional term to the left. So it's still upper bounded by this. You could write this plus the term t times that, but but I'm not exploiting it. I'm just using this fact. So okay. So now you have under C you have this, and then you also have again fx minus fx star is less than or equal to gradient of fx x minus x star minus small m times x minus x star square over 2. So this is simply using the strong convexity, this. So there's nothing extra in here. And now you can further bound this by Okay. Gradient of fx square over 2m so what I'm doing here is I'm using the Cauchy-Schwarz on this with an additional constant factor. So you can multiply one of the terms by a constant and the other term by the reciprocal of that constant, and you still have the Cauchy-Schwarz. So you have here I write 2m, and then here I write x minus x star over square over 2 times m. Okay, so this m is here and here. And then you have minus m times x minus x star square over 2. So these two cancel out, and that is equal to gradient fx square over 2m. All right, so you got this bound on fx minus fx star in terms of the gradient fx square. And then in this case, you simply choose LT to be fxt minus fx star. And then you obtain that dLT over dt, which was already shown here that the derivative is this. So dLT over dt is simply minus norm of gradient fxt square. Okay, I forgot no, that's fine. And yeah, this is it. And then that's equal to minus 2m times LT from this. Okay, so immediately by Grunwald's lemma, you have that LT is less than or equal to exponential minus 2mt times L0. So f xt minus f x star is less than or equal to exponential minus 2mt times f x0 minus fx star. Okay, so in this case, as you can see, the convergence is very simple, and you can just use f as the Lyapunov function, which is like the simplest possible Lyapunov function you can expect. And now, when you do discretization, so to get some practical algorithms, you will need some additional assumptions to keep these rates. So first, I'm going to look at assumption A. So now, instead of only assuming that f is continuously differentiable and convex, I will also assume that the gradient of fx is m Lipschitz. So this is the necessary assumption. So under B, you have, when you're looking at the gradient descent, so xk minus s times gradient fxk, then if you define the Lyapunov function Lk as k times s times fxk minus fx star plus xk minus x star square over 2. So if you compare this with the Lyapunov function that we had here, you see it's not that different. The only thing that we do, we replace t by k times s. And you got the same thing. And now, when you compute ik plus 1 minus lk, our goal is to show that it's negative. So now first I'm going to compute the differences of these terms here. So first of all, you have xk plus 1 minus x star square minus xk minus x star square. This is equal to so basically I'm just going to write it in this way. So this is xk minus x star plus minus s times gradient fx k xk minus x star minus s times gradient fxk. Okay, and then you have minus xk minus x star, xk minus x star. Okay, so by rearrangement, you will get that this is equal to minus 2s times xk minus x star gradient f xk plus s squared times gradient f xk norm square. So that's it. And then for the function f, you have fxk plus 1 minus fxk is equal to okay, so you have you can write it as integral of gradient f xk plus t times xk plus 1 minus xk, okay, times xk plus 1 minus xk, and then by using the smoothness condition, so the diffuseness of the gradient, you can upper bound this by gradient fxk xk plus 1 minus xk plus m over 2 times xk plus 1 minus xk square. All right, so this is follows from the Lipschitz of gradient, and then again this is the same as gradient fxk times s. So after some combination, you will have that this is equal to minus s minus m over 2 times s square times gradient f xk square. And then this is obviously, so now I'm going to say that I'm going to assume that s is less than or equal to 1 over m. Okay? So under this assumption, this is less than or equal to minus s over 2 times gradient f xk norm square. So, all right? And then if you combine these two terms, then you will obtain that lk plus 1 minus lk equals to k plus 1 times s times f xk plus 1 minus fx star plus s times fxk minus fx star plus 1/2 times xk plus 1 minus x star square minus xk minus x star square. And okay, and then if you substitute these things inside, you will get some nice cancellations, and in the end you will get that this is less than or equal to k times s square times gradient f x k square over 2, and that is less than or equal to 0. So the only condition that we had is that s is less than or equal to 1 over m, and of course you need assumption b. So so this, what does this imply? This implies that fxk minus fx star is less than or equal to x0 minus x star square over 2 times k times s. Okay? This is a straightforward from the fact that Lk is less than or equal to L0, which is equal to this over 2. So, all right, so we have this nice Lyapunov function that was very similar to the continuous case. And now I'm going to look at the assumption C. So we have a strong convexity. So as we will see, this is again not enough to show convergence in discrete time. So you also need this M Lipschitzness. So now you have assumption D here. And assumption D is going to be the following. So again, you will have Lk as fxk minus fx star. And you choose S to be 1 over m. Then it's possible to show that for the gradient descent, you have Lk plus 1 less than or equal to 1 minus small m over 2 capital M times Lk. Okay? And so the proof is the following. So you have first step is that we are going to use the same bound on this quantity that we've found out here. So when you have when you substitute S to be 1 over capital M, then you will get that this whole thing is 1 over 2 capital M. So this is less than or equal to minus 1 over 2 capital M times gradient of f x k norm square. And then now using the result about strong convexity, so this result, you are able to bound this by minus small m over 2 capital M times gradient f x k times xk minus x star. And then this is obviously by convexity can be upper bounded by minus small m over 2m times fxk minus fx star, which is lk. So, and then this follows by rearrangement. So now we have looked at the gradient descent in discrete and continuous time. And now it's about time to look at the sampling counterpart. So this is the Langevin diffusion. So, all right, so what we are looking at is dxt equals to minus gradient of f xt plus square root of 2 times dbt. And bt is Brownian motion. Now, it can be shown that the stationary distribution of this process is mu, when, and then mu is proportional to the exponential minus fx. All right? So now our goal would be to show some convergence rates for this diffusion to the stationary distribution. So for this, we are going to use the Wasserstein distance. So the two Wasserstein distance of some distribution nu and mu is going to be the infimum of over couplings with marginal mu and mu. The expected value of x minus y square, and then you take square root. So now the way to bound the two Wasserstein distance will be to use coupling. So let dxt be a Langevin diffusion. And dyt is also Langevin diffusion. And they use the same Brownian noise. So this is called a synchronous coupling. Then the difference between the two diffusions is deterministic. So you can differentiate it, and what you get is that this is minus the gradient of fyt minus the gradient of fxt. Okay? And then, so now we will be interested in obtaining a bound on these two Wasserstein distance. So we also compute the derivative of the square of the norm of these. So dyt minus xt square over dt. All right, so this is minus yt minus xt, gradient of fyt minus gradient of fxt. All right. And now you might remember that we had such a term somewhere far away there. So it was this. So it's lower bounded by m times x minus y squared. So this is less than or equal to minus m times x t minus y t square. And so, therefore, from this, it immediately follows that the Wasserstein distance of any distribution mu, you use you apply this Markov process up to time t on mu, and you compare with the stationary distribution mu. So this will be upper bounded by the initial distance between the two distributions times exponential minus m over 2 times t. So the half comes from the fact that we look at square here. And all right, so this is very straightforward to show contraction rates in continuous time for this Langevin diffusion. And now I'm going to go to discrete time. So, right. So, so the simplest way to discretize the Langevin diffusion is to use the Euler scheme. So simply we let xk plus 1 equals to xk minus h times gradient of fxk plus square root of 2h times z k plus 1, where zk plus 1 is standard normal d-dimensional. And now this Markov chain is not going to take mu as its stationary distribution, but we have a bias. But a good thing about this is that even though the bias is there, at least the convergence rate remains. So you still have a geometric rate as previously in continuous time. And this theorem by Dalayan, 2017, user-friendly, okay, guarantees, yeah. Okay, for Langevin diffusions. So under C, okay, so we only need under D. So we need both assumptions, continuous, okay, strong convexity and smoothness. So under D, if your discretization step size h satisfies that this is less than 2 times small m plus capital M, then the Wasserstein distance between k step and mu will be upper bounded by 1 minus small m times h to the kth power times v2 mu plus 1.65 times capital M over small m times h times the dimension d to the 1/2. Okay, so that is the result. So if you can, it's clear that the first term is almost the same as we had before, because you had also a convergence rate in terms of small m. So if you multiply by t, you would expect the same thing to hold with h. But the second term is different. So so this is a bias. This is the term quantifies the fact that no matter how many steps you make, you still cannot converge to the target mu. So now I'm going to sketch the proof of this. So the main idea is that we are going to construct a coupling between the diffusion that targets the correct distribution mu and the Markov chain. And by quantifying the distance between these two, we are able to obtain such a bound. So, okay, so you have the following proposition holds. Okay. Okay. So okay. And then alpha equals to 1.65. So this is a recursive bound on the distance between the k plus 1 step and the k step. So from this bound, you can obtain the result by some algebra. So to obtain such a result here, you will first construct this coupling between the diffusion and the Markov chain. So let L0 be a random vector sampled from mu, okay, coupled with xk, such that expectation of xk minus L0 square equals to the 2 Wasserstein distance square. Okay, so this is a so-called optimal coupling, and in Villani's book about optimal transport, he proves that it exists. So we can use this coupling that reaches the Wasserstein distance at step k, and from this you start a Brownian motion W. Okay, this is a Brownian motion such that WH equals to square root of h times z k plus 1. Okay, and WT is independent of xk and L0 for every t. Okay, so it's easy to see that such a Brownian motion exists, and then you define LT to be the Langevin diffusion with okay, driven by this Brownian motion. Okay. Yeah. So yeah, it's written now in this integral form, but you could also write differential form. And LH in particular equals to L0 minus integral from 0 to h gradient f ls ds plus square root of 2h times z k plus 1. And so because this is a diffusion process with stationary distribution mu, so if we start L0 to be yeah, so L0 is distributed as mu as well. So at each time LT is also going to be stationary and distributed according to mu. So now let delta k be the difference between L0 and xk, and delta k plus 1 is the difference between LH minus xk plus 1. Okay, just to remind you, so L0 and LH are both distributed according to mu. L0 is the coupling coupled together with xk by the optimal coupling, and we have defined LH to be driven by this diffusion, and now the idea is that we want to use this coupling to bound delta k plus 1, and through delta k plus 1 the Wasserstein distance at time k plus 1. So because obviously you have the Wasserstein distance between mu k plus 1 and mu is less than or equal to the expected value of delta k plus 1 square. Okay, so now we need to do some analysis here. So delta k plus 1 can be decomposed as delta k minus the integral from 0 to h gradient f ls ds plus h times the gradient f xk. Okay, so this is just by comparing this with xk plus 1, which is was defined here. Okay, so of course these two terms with z cancel out, for example, and you're left with this. And now this can be further written as delta k minus h times gradient of f L0 minus gradient of f xk minus integral from 0 to h gradient of f ls minus gradient of f L0. Okay, so ds. So now you have these two terms to bound, and first of all, it can be so it can be shown that the norm of delta k minus h times gradient of f L0 minus gradient of f xk. All right. So this is let's say equal to 1 minus m times h times gradient of k, delta k, sorry, norm. And it can be also shown that if you denote this quantity by v, then the expected value of v square is less than equal to 1/2 times h to the 4th cube. Okay. So using these bounds and some algebra, you can obtain the proposition here, and then by some more algebra you get this. So and showing these is again and it's just a bit of calculation, but there's no additional ideas there. So all right. So so it's nice, and because the proof is quite short, so it's also possible to adapt this to work with stochastic gradients and still obtain rates. Of course, if you use stochastic gradients, then the bias might increase if your variability in the gradients is very large. But the convergence rate is still similar here. So now I'm moving on to the next step, which is Nesterov's accelerated gradient descent. So okay. So for the gradient descent itself, if you only assume continuous differentiability, convexity, and M smoothness, we were only able to obtain rate 1/t for the gradient descent. But Nesterov has shown that he has shown that under assumption B, it is possible to obtain rate order 1/t square. So here is the algorithm. So first you set x1 equals to x0, and k greater than or equal to 2. You set yk to be xk minus 1 plus k minus 2 over k plus 1 times xk minus 1 minus xk minus 2, and the xk equals to xk minus 1, no, sorry, xk is equal to yk minus s times gradient of f yk. So instead of only one step, you have an additional step here, which in terms of y, so it's a sort of two-step method, because you are using k minus 1 and k minus 2 as well for forming the next iterate xk. And that's done in a way to accelerate convergence. So it can be shown that if S is less than or equal to 1 over m, then and B holds, then you have fxk minus fx star less than or equal to 2 times x0 minus x star square over s times k plus 1 square. Okay, so you have a square here compared to the linear k plus 1 rate before. And the first proof of this method was kind of difficult to understand because they were using various tricks and it wasn't really clear what's going on. But recently, in a paper by Candace, Bold, and Su, they have obtained the continuous time limit, and through this continuous time limit, they also had a very clean proof for the discrete time algorithm. So, okay, so there's this paper by Su, Boyd, and Candace, 2014. Okay, so what they have shown is that the ODE limit as s tends to 0 is of the following form: the second derivative of xt plus 3 over t times the first derivative of xt plus gradient f xt equals to 0, x okay, and then x derivative 0 is 0. Okay, so this was the recent result that really became very popular, and since 2014 there are more than 200 people who cited this, and basically one paper is coming out per week for in this type of area where you are looking at continuous time limit of optimization algorithms. And so if you have assumption A, then you can select the Lyapunov function Lt as t squared times f xt minus f x star plus 2 times xt minus xt plus t times x derivative t over 2 minus x star square. So it's possible to show that L derivative t is less than or equal to 0. So that implies that f xt minus f x star is less than or equal to 2 times x0 minus x star square over t. So times t square, sorry. Yeah, so this is very clear from the form of the Lyapunov function Lt. And there's also a way to select a variant of this function in discrete time, and that will imply this result. So I'm going to spare you with the proof of this. So now what's interesting here is that somehow this constant free appears out of nowhere, and people like Mike Jordan thought about this, whether you could choose it something else than free. And indeed, there's an interesting theory that they've developed that incorporates this case as a special case. So this is by Bibisono, Wilson, Jordan, 2016. So what they do is to generalize the ODE limit. So first, for smooth convex function H, okay, so again RD to R, such that you need to make sure that the gradient of H tends to infinity as x tends to infinity, and the Bragman divergence of y and x is defined as dhyx equals to hy minus hx minus gradient of fx y minus x. Oh, this is a nice end. Okay, so this is a sort of measure of the strong convexity of the function, because this is exactly what we bound, lower bound by this quantity here when assuming strong convexity. But in general, even for non-strongly convex functions, this quantity can be defined, and it's a sort of measures how non-strongly convex it is, and it's a sort of distance function between y and x as well. But in the sorry, that's wrong. It's h. Yeah. So if you have h x equals to x squared, then dhyx is just the square of y minus x. Okay, so that's kind of simple, and but there are more general cases to consider as well. So now they define the Bragman Lagrangian as xt, vt, t, okay, equals to exponential alpha t plus gamma t times dh, okay, xt plus e to the minus alpha t times vt xt, okay, and then there's an additional term here, minus e to the beta t times fxt. All right, so this is it. And now if you here, alpha t, beta t, gamma t are functions of t. Okay, and we want them to satisfy the conditions that beta t derivative is less than or equal to e to the alpha t, and gamma t equals to e to the alpha t. All right, so and then we define the energy function Jx as the integral from time 0 to capital T of the Lagrangian. Okay? So this is a function of the whole path. And it's called the energy function of the path. And the minimizer of this energy function satisfies the Euler Lagrange equations. Okay, which is xt second derivative plus e to the alpha t minus alpha derivative t times x derivative t plus e to the 2 alpha t plus beta t times the Hessian of h at xt plus e to the minus alpha t x derivative t inverse times gradient of h xt, okay, plus e to the minus alpha t times x derivative t minus gradient of h xt. All right, so this whole thing has to be equal to 0. So now if you and the good thing about this whole formalism is that if you define your OD in this way, then this fact that it's the minimizer of this J, it allows you to define a Lyapunov function automatically, which will be T equals to dH x star xt plus e to the minus alpha t times xt derivative plus e to the beta t times fx t minus fx star. So this is the Lyapunov function, and it satisfies that the derivative of this is less than or equal to 0, and that implies that the convergence rate is less than or equal to order e to the minus b beta t. Okay? So, all right, so there's a general formalism here that allows you to get convergence rate of arbitrary order, but this is not saying that you can discretize it and make useful algorithms. So you need to have some more about that. So first, if you choose alpha t to be log p minus log t, beta t equals to the, okay, this is the dimension log d minus, no, it's a parameter p. So you write it minus log p minus log t. So beta t will be chosen as p times log t plus log c, and gamma t is p times log t. So if you choose this, then the ODE simplifies, and what you get is the x second derivative t plus p plus 1 over 2 times x derivative t plus c times p square times t to the p minus 2 times, okay, this is a Hessian of h xt plus t over p times xt derivative inverse times the gradient of fxt. Okay, so this whole thing is 0. And what's nice about this is that if you choose p equal to, let me see, this is not 2, it's t. So if you choose p equal to 2, you and the capital C equal to 1, and h to be the square, so the norm square, then you end up with the same limit as here, because the Hessian of h will disappear, and all of these will disappear as well. Okay, so you have to choose C to be 1 over 4, then it will kill this. And now, the point of looking at this equation is that you can choose p equal to something else as well. And if you choose p an integer that's larger than or equal to 3, then what's interesting is that there is a discretization of this, such that if you assume assuming order p minus 1 smoothness, okay, so this means that if you differentiate your function p minus 1 times, it's going to be Lipschitz, your function f. So you can come up with a discretization that has convergence rate order k times s to the minus p. Okay? So you need to have a different type of assumption than B, which was only assuming first order smoothness. If you have higher order smoothness but no strong convexity, then you can get better rates by this discretization than with Nesterov's accelerated gradient descent. So it's still an open question whether there are discretizations that also achieve this rate, but computationally scalable to high dimensions. Because the current one that they propose, it involves solving a multivariate polynomial equation at each step. So it doesn't scale that well in dimensions. But maybe there's a way to do that. It's not yet known. But still, this is a very recent work in 2016, and they managed to improve upon something that's been in the literature for more than 20 years. So, okay. So I guess, what is the time now? Oh, so I have to, okay, so I have 20 more minutes to cover, okay, before the break. But, okay, do you have any questions at this point?
So, with claim and thinking, I'm not really an expert in this stuff, but I feel like it's a little bit cheating. Because, right now we're writing as a diffusion, like a continuous limit, right? So, essentially, you can actually just speed it up by this,
Yeah, of course.
T, right? And that's why it's kind of cheating, because you have a T to the power P minus 2 over there. So, actually, you just, you're just changing the time variable by because it was different. And you're thinking it's faster, but actually it doesn't have to be.
No, so yes, just proving something for continuous time is useless unless you have discretization as well, which is the difficult part, and that is where it's crucial to get your assumptions right. And but what's good is that about the continuous time is that just by looking the ODE solutions, you can get a feeling whether this can be discretized or not. If it's like super wavy and almost takes forever to solve by the ODE solver, there's a chance that even if it converges fast, it's useless because you can't discretize it in a reasonable amount of work. But if you get something very smooth and that converges fast as well, then there's a chance that you can discretize it somehow in an efficient way. So yes, you are right that just from the fact that it's fast, it doesn't mean anything. What you need to look at is the sort of how much waviness is in there within the time step h. So if it's well behaved within h, there's a chance that you can find a discretization that's accurate enough and gets the same convergence as the continuous time process. Yeah. So that's my intuition about this. Okay. All right. So do you have any other questions? Yes?
Is it really equal between going between gamma t and exponential alpha t? Or is
Yeah, it's equal. So, this is what is in their paper. So, under this assumption, you can show that the Lyapunov function defined in this way is decreasing. So I guess somewhere it has to be used this assumption to cancel out some terms, but.
the example you gave is that.
Oh, yeah. So let me look at this. So gamma t e to the alpha t log p. Okay. Maybe there's okay, I have to look at this. Yeah. Okay, I will figure out, check this in the break, but yeah, one of those are not correct, but I will figure out which one in the break. So, okay. Any other questions? Okay, so if not, then I will move on to the next one, which is the heavy ball method. And okay, so yeah. Now maybe start from here. So, uh, okay, so consider the following procedure. So xk plus 1 equals to xk plus s times pk, and pk plus 1 equals to minus gradient of f xk plus 1 times s minus 1 minus gamma s times pk. Okay, so what does this describe? So pk is momentum. So you have sort of moving according to the momentum, and the momentum is updated according to the gradient of f, which is like the force term, and then you have this term which is the sort of the friction. So in continuous time, this has the ODE limit that xt derivative is equal to pt, and pt derivative is equal to minus gradient of fxt minus gamma times pt. Okay, so this is a sort of corresponding to the friction term. So pt is decreasing by friction, and xt is moving according to pt. So it's sort of similar to the Hamiltonian dynamics, but you have this additional friction term here. And now, under assumption C, so we assume that you have a strong convexity. You can show that if you choose L, okay, xt, pt as fx minus fx star plus pt square over 2 plus some constant c that's positive times t minus x star pt. Then you can show that the derivative of this is less than equal to minus lambda times L xt pt. Okay, so you have a geometric convergence rate. Now and then you can get similarly geometric or linear rates for the discrete version of this using the same type of function here. Now, so this is a method that's very popular these days in deep learning as well, because it's very highly suitable for using stochastic gradients instead of deterministic gradients. And in those cases, it still shows a good performance. And one interesting feature of this is that when you are applying this to a quadratic function, then you can show by a slightly more complicated method than this Lyapunov function here, is you can show that the convergence rate is proportional to the square root of the condition number. So it's faster than the gradient descent, and it's the same as the preconditioned conjugate gradients. So it's the same rate as conjugate gradients for quadratic functions. And this means that also when you get near the minimum, every function that's strongly convex is quadratic. So there you have a fast rate. So that these are some attractive features of this method.
What is lambda there?
Lambda is a positive constant. So,
How does it depend on
well, it's. I'm going to talk about this more in my next talk on the 20th of September. But there's a relation. So it's a bit long, the formulas here. So I'm going to spare you with that. But why this is important in statistics is that you can use the SD limit of this process for sampling. So in this case, the SD limit okay, so the SD for this is dxt equals to pt dt, dpt equals to minus u times the gradient of f xt dt minus gamma times p t dt plus square root of 2 times gamma times u times dbt. So this is just a d-dimensional Brownian motion. So now you can show that mu proportional to exponential minus fx is the stationary distribution. And yeah. So now I'm going to look at the convergence rate to the stationary distribution. So if you have two processes, xt1, pt1, and xt2, pt2, and these are two paths, okay, using the same bt, okay, and I'm going to denote by xt tilde the difference between the x components and pt tilde the difference between the p components. And then you can show that these satisfy the equations that d over dt xt tilde equals to pt tilde and d over dt pt tilde equals to minus gamma times pt tilde minus u times gradient of f xt2 minus gradient of f xt1. Okay, so this is slightly annoying because you have something that's not explicitly expressible just in terms of x tilde and p tilde. But you can rewrite this as you can still write this as minus gamma times pt tilde minus u times h t times xt tilde, where ht is a d times d matrix that's written as the integral from 0 to 1 of the Hessian of xt1 plus okay, r times xt2 minus xt1. Okay, so you just average out the Hessian of f from xt1 to xt2, and you can write the evolution of pt tilde in this form with this matrix. And all right. And then you can see that this matrix satisfies that it's between capital M times the identity and small m times the identity in positive semi-definite order. Because, okay, you under assumption D, so we are going to look at strongly convex and smooth functions. Okay, so all right, so I guess we still have 10 minutes. So now, if you have this form here, so yeah, so that is the key. So now we are going to look at the Lyapunov function Lt, which is simply the sum of squares. So first you have xt square, and then you have xt tilde plus pt tilde square. And then you can show that this Lyapunov function can be differentiated, and the derivative can be written in the form of minus 2 times, okay, so xt okay, so the transpose of this times gamma minus 1 times identity minus identity u times ht minus gamma minus 1 times identity and identity. And then you need to multiply this again by xt tilde plus pt tilde xt tilde. Okay, so this is from the left, this is from the right. And this is the matrix that's crucial. So identity is a d-dimensional identity matrix everywhere. So now, if you want to show that this Lt is contracting at a linear rate, all you need to show is that this matrix is lower bounded by a constant times the identity. And because the way the Lyapunov function was defined is simply the square of the norm of this.
Good question. So,
yeah.
Since you're doing the quadratic form, why do you make it non-symmetric?
Oh, yeah. Okay, so that's the next step. Yeah, okay. So I could have written it directly in a symmetric way. Anyway, so that's a good point. So you're going to rewrite this as qt equals to the symmetrized version. Transpose over 2. And so our goal is to show that qt is positive definite. And to do that, you just compute its eigenvalues, and by some it's easy to show that the eigenvalues of qt satisfy that the determinant of gamma minus 1 minus lambda times 1 minus lambda times the identity minus 1 over 4th times u times ht minus gamma times the identity square. Okay, so this determinant is 0. And if you choose gamma to be 2 and u to be 1 over capital M, then this leads to lambda j equals to 1 plus minus 1 minus capital lambda j over 2m, where capital lambda j is the eigenvalues of ht. So we know that capital lambda j is between small m and capital M. So this implies that minimum of lambda j is greater than or equal to small m over capital M divided by 2. So we will call this kappa, and this implies that d over dt lt is less than or equal to minus kappa over 2 lt. So you have a convergence with this rate. And it's straightforward to show that this implies that the Wasserstein 2 distance of P2 nu, okay, less than or equal to some constant times the e to the minus t times kappa over 2 times the Wasserstein 2 distance of nu and nu. Okay, so all right, there's a 4 here, but the constant is because the Wasserstein 2 norm is slightly different from this norm, but it's equivalent up to a constant factor. Okay, so that is the convergence rate for the SDE. That's called the underdamped Langevin diffusion. So this SDE is called the underdamped . Okay, and the proof I just show you is by a paper by Jordan. Okay, let me see the, yes, so it's a recent paper, 2016. All right, so I guess it's 3:40 now, so we can take a break and come back later. Okay? Thank you. Yeah.
Anyone want to ask any questions or take a break? Let's thank Daniel.
Okay, thank you.